This video covers Griffiths E&M 1.3.1, the beginning of the section talking about line integrals. So throughout this course, we will have to not only take derivatives of vector fields, but we're also going to need to integrate them. And there's a couple of different ways that we can integrate a vector field. The first is by calculating what is called a line integral. You'll have some vector field v, and you'll want to know how that vector field changes as you move from point A to point B in some space following some path. Okay, so the integral will have bounds of A and B, moving from A to B, and we're going to evaluate what that field is dotted with the path that we take. Right? Remember, dl here is our infinitesimal displacement vector, and v is our field. So in principle, we can take any number of paths that we want. We could take the path that's written in black, or we could take some other path from A to B, right? And we could perhaps call that dl2 in red. Right? And in that case, we would want to go from A to B, or bounds would still be the same. We'd still have the same vector field, but we would instead dot that with our infinitesimal displacement vector dl2. Occasionally, we will be interested in what happens to our path as we go, following some trajectory, but ending at the exact same place that we began. In that case, we call this a closed path, and we denote that by the circle, or our closed path, v dot dl. Now, in general, this closed path integral can take on any number of, and it can take on any value. However, there are particular types of vector fields where this closed loop yields 0. All right. If that's true, that means that the path taken is independent. Or rather, it doesn't matter which path you take from point A to point B. This line integral will be 0. And you've probably talked about things like this in the past. You may not have known, but in the case of things that are conservative, forces that are conservative, if you take the path integral, if you take this integral along different trajectories in some force field, you'll find that it doesn't matter the path you take. Okay, so let's go ahead and do an example here. This is figure 1.2.1, example 1.6. I have a 2D plane, x, y. I have 2 points. I'm starting from 1, 1, and I'm ending at 2, 2, and I can pick any trajectory that I want. Right? Well, it doesn't matter which direction I go from point A to point B, but for the sake of mathematically simple paths, we're going to choose 2. The first path we're going to take is going to be along the x direction first. Once I get to point 2, 1, I will then go up to point 2, 2. The second direction I'm going to take is just the straightest path from 1, 1 to 2, 2. Okay, so let's calculate the path integral along each of these different paths, and let's see if there's a difference. So generically, I have my infinitesimal displacement vector, dx in the x hat plus dy in the y hat plus dz in the z hat. Okay, I'm going to talk about going along this blue path first, but I have to split this path into two subpaths. Call that I and II. In this path I specify that now we're talking about the blue path explicitly. This infinitesimal displacement vector, right? In principle, I have dx, dy, and dz, but x, y, and z are not changing, right? So my infinitesimal displacement vector reduces to dx in the x hat direction because dy is 0. I'm not changing in y as I move along this direction. All right, at this height, my value for y is equal to 1. And I can calculate this integral v dot dl. I forgot to say what v was. V here, the field for both cases, is going to be y squared in the x hat direction plus 2x y plus 1 in the y hat direction. Okay, so v dot dl then becomes y squared x hat plus 2x y plus 1 y hat dotted with dx x hat. All right, dot products only select like terms, so I'm left with just the x hat components. I'll leave the integral because I haven't taken the integral yet. I'm left with y squared dx. All right, and I haven't put bounds on that integral yet, but dx is the only component I'm changing, right? So and x is moving from 1 to 2. I haven't filled in what y is yet, so I'll do that. 1 to 2, y is 1, so this is just dx. So I'm left with 1. Okay, so that's the component from the first part of my path. In the end, we're going to add all of those up. Okay, so now my second part of my path. All right, let's see what that is. DL here is now dx. X is not changing, so I don't have any dx. Now y is changing, so now I'm left with dy in the y hat direction, and dz is not an issue here. I also know that at this position, x is equal to 2. Okay, so I can do my integral v dot dl. My bounds let's do the next step first. My integral is going to be y squared x hat plus 2x y plus 1 in the y hat dotted with dl. dl is just dy in the y hat direction, so I'm going to pick up this component of my dot product, and I'm left with 2x y plus 1 dy. Okay, so now let's put the bounds on, since now we're talking about y explicitly. Y is going to go from 1 to 2, right? 1 to 2. X is equal to 2 here, so this is 4 y plus 1 dy from 1 to 2. And that gives me 10. So my total blue path integral gives me 1 plus 10 equals 11. Okay, so the story is a little bit different on path, on the red path. On the red path, my infinitesimal displacement vector is no longer just dx or dy, but it is both dx plus x hat plus dy in the y hat. I'm following a path that goes from points 1, 1 to points 2, 2. So that is along the line y equals x, which makes it convenient. So our derivative dy is equal to dx. Right? If you choose a more complicated path, this expression is going to be kind of difficult to deal with. So you should know the functional form of the path you're taking. All right. So since dy is equal to dx, I can go ahead and rewrite dl as dx in the x hat direction plus dx in the y hat direction. Right. Dx is equal to dy. I can just plug it in here. So now my integral v dot dl is y squared x hat plus 2x y plus 1 in the y hat direction, dotted with dx x hat plus dx y hat. Okay, so x hats become y squared dx plus 2xy plus 1 dx. Okay, those are both the same integral, so technically I don't need to do another integrand. All right, now I can go ahead and plug in y's are related to x's, so everything's in terms of x's. This becomes x squared plus 2x x plus 1 dx. And what is x changing from? X is changing from 1 to 2. I can go ahead and do that integral, and in the end, I get 10, I believe. Okay, so this function here, this vector field is depends on the direction, the path that you take. All right, our total path 10 is not the same as our path 11.